thanks to everybody who made it for the last lecture. So let me remind you what we were doing last time. So our goal was to show that if you have M n-dimensional and at least 3, analytic and Riemannian, and if negatively curved, and compact, if there exist infinitely many immersed totally geodesic, let's say compact, as J into M, then M was isometric to a quotient of hyperbolic space. So we had the diagram, we had M, we had the unit tangent bundle, and we had the hyperplane bundle, and we had the set where these two things were incident. So UM was the unit tangent bundle, HM was the oriented hyperplane bundle, and FM was the set of pairs V1 and V2, unit orthogonal vectors. So this is over a fixed point in M. You take unit orthogonal vectors in the tangent space, and then you put them together in a fibration, and you have a forgetful map by for getting V2, you map to the unit tangent bundle, and by forgetting V1, you take the hyperplane associated to the orthogonal V2. All right. So associated to this, we had 3 more sets. So Z was the totally geodesic hyperplanes that exponentiate to a totally geodesic hypersurface, not necessarily closed. I was, so we had names for these maps, pi H and pi U. I was pi H inverse of Z, and A was pi U of I. So we had 3 steps. A is everything. Z is everything. And then step 3, we're done by this theorem of Cartan. So we did this last time. And today I want to explain some of the ingredients that go into step 2. So maybe one remark is that to do step 1, we only worked with A in some sense, and we were only interested in the geodesic flow on the unit tangent bundle, which had this hyperbolicity. And to deal with step 2, we're going to have to consider an extension of the geodesic flow. So I'll explain all of this today. But before I proceed, let me ask if there are any questions, or if I forgot another assumption again. OK. So for step 2, step 2 is also going to be dynamical. So I'm going to first outline the proof, and I'll make an assumption, and I'll explain what the assumption is, and then I'll try to develop it and try to explain how this is established. So, so we look over a point, let me say x and m. So then the fiber, this is isomorphic to the n-1 sphere, and the same thing for hm of x, and that's n-1 sphere. And fm over either of these, or hm, is an Sn-2 fibration. So the fibers are these Sn-2s. So we have this as n-1, Sn-1, and we have here, so let me call this, so Fm fiber over x, again, pi h and pi u. So we have our set here, z intersected with Fm of x. So what do we know about z? So the first, we know quite a few things. So we know about z. So it is closed and GT invariant. So I have not explained this yet, but we'll see in a moment that there's a way to lift the geodesic flow to a flow on this larger space of incident pairs. So it's closed and GT invariant for a lift of the geodesic flow, little GT. We know a few more things. So we have that z projects surjectively to, so let me call this z of x. This is going to be notation for z intersected with Fm of x. So this projects surjectively onto along pi h. So if I project it in this direction, it's everything. So it has full image. It's also saturated by the fibers of, sorry, here, of course, I said it projects surjectively along pi u, right, not pi h. So I apologize if you already wrote h, so it's pi u. And now on the other side, in the pi h direction, it is saturated by the fibers of pi h. So what does this mean geometrically? It simply means that if I take a hyperplane here, so remember, a point in here I think of as a hyperplane, the fibers are all the unit vectors that are contained in that hyperplane. So by definition of z, z is the preimage of something in here. So that's OK. Yeah. Sorry, can you say louder?
So the definition of Zx, is it the intersection of Z with Mx or the preimage of Z? I think Z is a subset of.
Oh, you want A?
Right?
You want A not Z?
Let me see. A. Oh, sorry. I mean I. I apologize. I don't know why I keep. Yeah. So here the set is supposed to be I. Yes. So I apologize. So our ultimate goal is to show that I is everything, but we're going to instead show that Z is everything. That's why, sorry. Our goal is to show that Z is everything, but we're going to just show that I is everything. Yes. So now, yeah. So I is the incident set, and yeah. Okay, and there's one more crucial input that I will use, which is that the fibers of pi u are saturated by orbits of a group, let me call this BU, so U here belongs to this S, the unit sphere of the tangent bundle, and BU is inside the orthogonal, the orthogonal group of U perp, so where U perp is inside as so in this direction, I'm just I is fully saturated along the fibers. In this direction, I'd like to say that ideally, and we would like to know that maybe it's saturated by the fibers in this direction as well. And if we knew that, we would be essentially done. But the only thing what I'll try to explain now or next is that it is saturated by the orbit of a group, which is fairly large, but not quite the full group. So, so this BU depends continuously on U in this unit sphere, and is quite large. So we will show that BU, if I look at BU acting on the unit sphere of U perp, then there's two possibilities. It's either a point, so in other words, either the action is transitive, or it is an interval. So the space of orbits, it's essentially like the orthogonal group of one dimension less acting on the unit sphere by rotations. Okay, so once you have this information, you're basically you just have to play a little bit with this diagram and doing some games excuse me, that I'll explain, analogous games in a minute, and you can conclude from this that I really has to be everything. So you have this subset in each fiber, which on the one hand is saturated by the fibers of one fibration, and on the other hand, along the other fibration, it's almost saturated by the fibers. And you just start with one point, you project, you get a lot of points, and then you keep doing some incidence games, and eventually you reach the conclusion that the only way that this can happen is that I is the whole set. So I know this is a little bit vague, but I want to explain some arguments which first of all, I want to explain where this group comes from and how you can constrain this group and show that it can be fairly large. And this, I think, hopefully will give you some flavor of how these kind of arguments go, okay, with these double fibrations. All right? So any questions? Yeah, so that's a good point. So nothing in this argument uses the analytic property. Yeah, so analyticity is only used in step 1. But to get that this group B is fairly large, you don't need analyticity. But if you remember, I hinted at this question that you might want to assume not that there's infinitely many closed-totally geodesic submanifolds, but rather that there is only one, but it doesn't have to be, but which is definitely not closed, so that there's some accumulation. So the first step works with that assumption as well, but in the second step you have some issues with that assumption, so it only works for certain particular dimensions, which I'll try to explain. So in order to explain where these things come from, I need to talk about frame flows. So if we have M as a Riemannian manifold, then I'm going to denote by PM the bundle of frames, full frames on M. So the fiber above a point X is going to be the set of n vectors which form an orthonormal basis. So this is the same as the set of orientation preserved. So let me say an oriented, just to be in the connected case. So it's an oriented orthonormal basis. And so this is the same as the set of oriented isometries from Rn onto this vector space. So, so Pm of x is a right SO and R torso. So let me, okay, so let me not introduce this yet. So SO and R act transitively on Pm of x by precomposition on the right. And SO of this tangent bundle also acts transitively. This is on the left. So you have this set of isometry of ways to identify your tangent space with a fixed model space like Rn, and you have a transitive, free and transitive action of the isometries of Rn, and also free and transitive action of the isometries of the tangent space. Okay. So this Pm of x, or Pm over M, is what's called a principal SO and R bundle, which is to say that it's a manifold equipped with a map such that and an action on the right of this group such that the action is transitive on the fibers, free and transitive. Okay. So UM is simply PM divided by the group SO n minus 1 R, where I act on the last n minus 1 elements. And so the geodesic flow on UM has a lift GT to PM, which commutes with the right action of SL minus 1. So what is this lift? It's given by parallel transport along the geodesic. Off the full frame. So kind of in pictures, if you have your geodesic, so this is your geodesic gamma, you have a tangent vector v1, and maybe you give yourself another tangent vector v2 and v3, and you can parallel transport them using the Levi-Civita connection, and you will get tangent here, tangent here. This is v1, v2. So you're parallel transporting them. They maybe get a little bit twisted, or some kind of interesting things can happen. But it's important that the fibers, the group SONR, or SN-1R, is a compact group. So things are not too bad. OK? So we already know, for example, that the Lebesgue measure for an Anosov flow, in particular for the geodesic flow, the Lebesgue measure is ergodic. So we would like to understand, for example, the ergodicity of these kinds of systems. Okay? So just notationally, it will be for a moment a little bit more convenient to take a step back and just consider a slightly more abstract setup, just so step away from geodesic flows. And more generally, we can consider compact extensions, compact group extensions of Anosov flows. So what I mean by this is the following. So we have a compact Lie group, maybe even connected if you want, K, and a principal K bundle P over M. And here we have a flow, and GT acting on P, and little gt acting on M. So we have these flows, and with the property that GT commutes with K, and little gt is Anosov. Right. So I'm going to also assume that gt is, if you either want to assume that, for example, it preserves a Lebesgue class measure, or it's transitive, meaning that it has at least one dense orbit. So hopefully I'll explain why this might not always be the case in general. But OK, so if you remember, so the stable and unstable manifolds of GT lift, so bundles and manifolds lift to P. So we have that the tangent space at some point little p of P, it has a decomposition. So we have the flow direction. So this is the flow direction. And then we have an unstable direction, the lift of the tangent unstable, the lift of the tangent stable. And then we have the vertical direction. Okay. So this is at the level of linear spaces, and some general theory tells you that there will be also stable and unstable foliations. So we also have W tilde stable of P, W tilde unstable of P. And now we have kind of an interesting structure. So, so let's say that this is on the base. This is the stables and unstables. And now I take a fiber. This is my P of x. This is the point x. And so these manifolds from the bottom, they lift so if I take 2 points over here, oops, so x and y, I have given y inside W, let's say unstable of x. So you can consider the local unstable, so everything is in some small neighborhood, although by acting using the dynamics, you can always arrange for 2 points to be close enough. So there's a map. So I'm going to call this HU from PX to PY. So this is HU of XY. Between the fibers, given by essentially drawing this unstable manifold through the, so if I have a point here, if I want to know which point do I want to connect it to, in the other fiber, I just draw the unstable manifold. And it's characterized by the property that if I take the flow, and if I take a point P, and I take its image under the holonomy, then this, oops, GT of P and GT of this image, this distance, it goes to 0 as because I took the unstable, it goes to, I have to send t to minus infinity. If I do the same on the stable, then they approach each other at plus infinity. Okay? So there's this way to identify fibers along stable manifolds and along unstable manifolds. So this map HU of XY commutes with the right action of K. Right? So I can do this along stables. essentially by construction along the flow direction. So here I don't have the flow direction in the picture, but I can go, for example, along an unstable, and then a stable, and then an unstable, and then maybe come back. And I would get a map from Px into itself, which commutes with the action of k. Right? So let me call, so it's a definition. CSU chain is a sequence x1 dot xn and m such that xi and xi plus 1 are either on the same stable, unstable, or flow line, and such a chain determines a map from the starting point to the end point. Yeah. Sorry, did I? Yeah, there's one thing I did which is not good among many other things, but it would have been better to call this manifold not M but U, right? Because the Anosov flow is on UM, not on M, right? So I apologize for this omission. You can either put UM in front. I think this will be better than erasing M everywhere and switching it to U. So, so let me call Bx. This is a definition. So Bx is defined to be the closure. Sorry, before, yeah, so let me say, so it's the closure in the set at Px. K, which is the set of maps F from Px to Px such that f of x times k equals f of x times k for any, sorry, f of p for any p in Px for any k in k. So this is B of x is the closure in this group of all transformations from Px into itself obtained along all possible CSU chains. Yeah, did I miss something? Or so let me note that this group that I wrote over here, this is a group that's isomorphic to K. So P of x is a right k-torsor, which means that it's essentially like a group without a base point. So you have that k acts transitively and freely on it, and if I fix some point p inside px, then this gives an isomorphism between this group that I wrote there, odd px that commutes with k and k. So you can think of p of x as essentially like an orthogonal group, but without a base point. So we had this example earlier that on the previous board, where if I had two vector spaces with positive definite quadratic forms, I have the set of possible isomorphisms. There's no choice of a canonical isomorphism, but I can act on the right using one change of bases, and I act transitively and freely, and I can act on the left using another change of bases, and I again act transitively and freely. Okay? So this is just kind of notation, but the point is that it's kind of a useful notational device. And okay. So any questions? So this group, the group B of x and these groups B of x prime are isomorphic for any x and x prime, and that are in the same path component. So of course, I'm going to assume that my manifold is connected, but not canonically so. So it really depends on how I choose to connect x and x prime by one of these CSU paths. Okay? So it's a little bit like the fundamental group, where if you choose a base point, you have a fundamental group, but if you choose a different base point, there's a different group isomorphic to the old one, but in a way that depends on how you choose the path. Okay. So okay. So now here's a proposition which is not very hard. So I'm going to say that x inside, so there exists at least one set x inside P which is closed, GT invariant, projects surjectively to M and is minimal with this property. So if you remember, if you have a dynamical system with a compact metric space, there's always at least one minimal set. So a closed set which is invariant by the dynamics. And the reason is that if you take a sequence of these things, that, an intersection of compact sets is compact. And here P is itself compact, but you don't even need to assume the base to be compact. You only need to assume that P is proper over the base. And then such a minimal set always exists by the same argument. And the second property is that such an x is fiber-wise the orbit of a subgroup H and B of U, B of X is conjugate to H for any X. So what I'm saying here is that you have your dynamical system here, so maybe this is your M, and you have this extension, so this is P sitting over M, and the fibers there, you have the transitive action of this group K, so K acts on this transitively, and there's a way to, if you choose the one such minimal set, you get a this. This is our minimal set X. So it's in each fiber, it's the orbit by acting on the right by a single group H. Okay, and it's the same group for every fiber. And you can think of this B of X as kind of the internal to this fiber acting, group acting on this. Okay? So maybe I should remark that this is not standard terminology, but B of X, we're gonna call this the Brin group. So Brin was one of the first people to study the ergodicity of frame flows and questions related to that. And he essentially defined something like the Brin group, although he was kind of more interested in the version of it that did not depend on the base point, this group H. And okay. So another general fact, which once you develop this formalism of these groups, is that so suppose so let me call this K1 inside K is a closed subgroup. For example, the trivial subgroup. Then closed, so or then ergodic GT, capital GT ergodic measures on P mod K1 that project to the volume measure on so I'm going to here on M, or we're really on UM, on the place where the dynamics happens, are in bijection with essentially, if I take this Brin group, B of X divided by P of X divided by K1 for any X. So it's this double coset space. In particular, if this Brin group is the largest it could be, for example, if it's all of, if the Brin group is all of K, then all of these actions are ergodic no matter what K1 is. If the Brin group is very small, then essentially none of them are ergodic except for the trivial action. So in general, you want to show that the Brin group is as large as possible. And if you're familiar with this terminology, the Brin group is something like the algebraic hull of some cocycle. So it's it's kind of the smallest set of restrictions that that any invariant object has to satisfy. So there's a nice theorem of Brin and Gromov, actually. So if you look at the original paper, apparently they're both based at the IHES at the time when they wrote the paper. So I guess Brin was visiting. So they showed that actually there's a non-trivial topological restriction that implies that in the case of geodesic flows, the Brin group a priori has to be quite large. It doesn't have to be everything, but it has to be quite large. So let me explain this. So if you have, so remember, we have UM sitting over PM sitting over M. So this is a sphere bundle. And PM, this is an SO n-1 bundle. And so this data of the Brin group is essentially the same thing as a map. So let me call this. So the Brin group is essentially the same as a map sigma from UM to PM divided by H, where H inside SO n-1R is conjugate to the Brin group. So this map is continuous. In fact, it's smooth, but we don't need this fact. So let me say 2 words about this. So why is it continuous? It's continuous because essentially this set X is closed. So the graph of this map, if you work out the definitions, it's a closed subset of this fiber bundle. So a function with closed graph is continuous. And smoothness is a little bit trickier, and it follows from the fact that essentially this section that defines this map sigma, it goes up. This map is smooth along the stable foliation, and it's smooth along the unstable foliation. And there's some general theorem called Journet's lemma that ensures that such a thing is therefore smooth in general. But we only need continuity. And so if we restrict to a fiber, we get a map to a fiber of the map from UM to M. So we get the map sigma of X from S n-1 to SO n-1. Sorry. So an S, so an R. And this is SO and R. 1 SO n minus 1. So we have such a map, and so we have a projection. So we clearly have a projection. So n r. So H is a subgroup of SON minus 1R, and the existence of this map, of a continuous such map, is a non-trivial topological abstraction. On the right. No, because I'm taking the I'm taking the fiber over point X.
Oh, you're taking the whole fiber over.
The whole fiber over X is SONR.
Okay.
And because I'm also taking here the whole sphere of such things.
Okay.
Yeah. Yeah, so I'm taking the whole abstraction comes from the fact that the underlying manifold for a geodesic flow is not any manifold, but it's it's the unit tangent bundle, which in particular has all these spheres. Okay. So from this you can get all sorts of topological abstractions, and things get. If you look in Brin and Gromov's paper, they come up with some kind of list of things that were known at that time. To when can such maps exist, just such continuous maps. In the meantime, things have improved a little bit more, and people know now more abstractions, but nonetheless, such maps can sometimes exist. I want to give you an example of why such a map, a situation where such a map cannot exist. And so here's a proposition. If n is odd, there does not exist a map continuous map from SO and R mod SO and minus 1R. Okay, so not the continuous map, but the continuous section of this projection. So this is a proposition which you can prove using first-year algebraic topology. So what is this space? Just the n minus 1 sphere, right? So this is isomorphic to Sn minus 1. And what is this space on the right? This is just the unit tangent bundle of that sphere. This is the unit tangent bundle of Sn minus 1. This is unit tangent bundle. And so I claim that there's no continuous map the other way, no section. So why is that? If n is odd? Huh? Yes, I don't know who said it, but someone said Poincare-Hopf. Exactly. So on an even dimensional sphere, there is no non-vanishing vector field. So no section, because on an even dimensional sphere, no non-vanishing vector field, because the Euler characteristic of Sn minus 1 is 1 plus minus 1 to the n minus 1, which when n is even is 2. Okay? So a corollary of this is that the two-frame flow on odd-dimensional negatively curved manifolds is ergodic with respect to volume. So what is the two-frame flow? This is so this two-frame flow over UM. This is the quotient. So we have PM. This is PM divided by SO n minus 2R. And this is, if you remember in our diagram, this is precisely the space that I called Fm. This is the same as Fm from previous argument. So at least in the odd-dimensional case, I've essentially given you a complete proof, modulo various translations, that that set I had to be everything. Okay. So to handle the general case, there's kind of two things you have to do. One is you have to squeeze more restrictions from the Brin group situation, and in general, there's not. It's for example, it's not true that the two-frame flow on even-dimensional negatively curved manifolds is ergodic. So this actually fails. So there are certain abstractions, but they're quite well understood. Nonetheless, you have enough information, enough restrictions on the Brin group to show that this kind of diagram that we had earlier does not allow for the set I to be anything but the whole thing. Okay? So maybe, given that it's a hot day and I only have technically 3 minutes till the end, I'm not going to say more about things like the natural conjectures that one could make based on that theorem. So what kind of things you can expect in higher codimension. I'm happy to discuss it with anybody who would like to know more. But I'll just stop here for now.
Question for Simion.
The condition that there exists infinitely many totally geodesic hypersurfaces is only able to show that dz is greater than n-1.
That's right. The dimension.
Is only
Yeah.
used.
Yeah, that was the only place that we used it, yes. And the analytic condition was used to be able to talk about dimension.
Consider this maybe a statement for architecture about if you have a dense, like a non-closed.
Non-closed one? Yeah, so in odd dimensions, this essentially follows from what I've said. There's all sorts of other things, like I forget the exact restriction it's, that we have in our paper. I think with the current knowledge about what's known about the Brin group, it's maybe when it's even, maybe not divisible by 4 or something like this, and not 134 or some. There's some what?
I think you got it.
Yeah. So there's some kind of odd condition like that having to do with some exceptional structures. There's a quite general conjecture about the Brin group itself, which is independently of this work, which is that the Brin group should be, so there's something called the holonomy group of a Riemannian manifold, and the conjecture would be that in negative curvature, the Brin group should be, so you have, so let me state it because actually I looked in Brin's paper and he does not state this conjecture, and it's unfortunate that, because I think he means it in some sense, but you have, let me call this h of x, or h of x inside the orthogonal group of, so this is the Riemannian holonomy group. And the possibilities for this group are known and very short. So there's a classification of Berger of what these groups can be. And your manifold is either locally symmetric, or this group has to be one of 3 infinite families and 2 exceptional possibilities. And then, let's say, the question is the Brin group at a point u equal to this h of x intersected with the stabilizer with SO u perp. So now u is a tangent vector in x sitting above x, and I take this holonomy group and I intersect it with the perpendicular. And so this containment is by construction, so it cannot be larger than this. You can see, I didn't talk too much about how this construction is made, but you can see that you can realize essentially all of these S transports and U transports using holonomy. And so then the real question becomes whether this group can be strictly smaller. And as you can see from these arguments of Brin and Gromov, it already has to be quite large because of these topological restrictions, but there's still some a priori possibilities that you cannot exclude purely on topological grounds. So once you would know that, for example, once you knew this statement purely about frame flows, I think the statement about a single non-closed totally geodesic thing would, for example, follow. And I should add, this conjecture is known in various degrees of generality, but people need to assume something about the curvature, the size, like the K0 and the K1 from 2 lectures ago, like how pinched the curvature is. So if you assume that it's with the right pinching, you can derive this conclusion, but in increasingly better and better generality. But still, you could have not very pinched curvature, and the holonomy group could still be h of x. So I think pinching is not, I think, to my mind, the right condition.
Other questions? If not, thanks a million.